Hello everyone, I'm going to present you this session as a part of my final project submission for the course Probability Theory. So as a part of this session, I'm going to discuss about the concepts that were discussed in the classroom. So uh, I'm going to apply all those concepts uh, to the data set which I have taken from the Kaggle. So this data set is nothing but baseball players' height or weight prediction. So in this data set, we have six columns, namely, we have the column name, team, position, height in inches, weight in pounds, age. So these six columns gives us the information related to baseball players, and let us check the description of each and every column below the set. So here we have the name column which gives us the MLB player name. MLB is nothing but Major League Baseball players. And also we have team column. This team column is telling us the information related to the baseball team the player was a member of at the time the data was acquired. And we also have a position which gives us the player field position and height in inches, weight in pounds, and player age at the time of record. So in this data set we have 1032 records, unique values, and we have six columns. So let us pull this data set into our environment and perform various actions that were discussed in the classroom on this data set. So without getting delayed, let's go to our studio and pull the data set. I have downloaded this data set earlier on my local machine, so I'm just going to fetch the file path. From there I'm going to read the data set. So I'm just copying and pasting it over here. Let us run this command, uh, players, so that, yeah, so that here you could see that we have 1034 observations of six variables. So let us check what's there in the data. Head of players, that gives us the first five records that are present in the data set. So we have name, team, position, height in inches, weight in pounds, age. So these names are of different player names, and teams are different again, and position. uh, and these are numerical values that we can see over here. So let us check this nature of the columns that are in our data set. Str of players gives us the nature of column. So here in our data frame, we could see that name column is of character type and team column is of character type. Position is also of character type, and height and weight are of integer type, and age is numeric type. So it is good to see we can perform some actions on this age, height, weight, and also we can classify the players based on the catcher or first baseman based on the position, literally. So that's what our data set is. I think we are not going to use much of these teams and names, so we are not bothered about the name and team, because in this analysis I'm going to concentrate on the age, height, weight, because if you see, I'm just going to draw the conclusions between these three factors. So let's proceed further and check what else we can do here. So in this data set, there might be the values of NA, right? So in order to check the values of NA, I'm just using one command to know the uh, NA values, which gives us the valuable information uh, while interpreting the data. So check NA values column wise. So this can be done with the help of call sums of is dot na. So so is dot na which requires one. So sorry, I did not pass the data set itself. That's so funny. So I'm just going to give here players. So here you could see in the name column there are zero NA values, team column zero NA values, and in the position or height columns there are zero. And if you could observe, there is one NA value in the weight column. So we're just going to remove that one NA value and replace it with the zero, as the weight column is a integer column. So if some column is a character kind of column, I'm going to replace it with some space or else some null value. So but whereas here we have the integer column, hence I'm going to replace it with zero. So how can we do that replacement? I'm just pipelining players information. Just I'm storing in a variable called players, and I'm just pipelining this players data to replace function is dot na of dot comma 0. So this will replace the na values to 0, and error in players replace is dot na comma 0. Oh, there is some issue. What's the issue? What's the issue? So this is basically telling us that uh, it could not find the function, uh, this tidyverse function. I think I need to load the library of tidyverse over here. So let me load it and try again. Library of tidyverse. So so I just loaded the function library, and okay. So now it's running. And now let us check for call sums of players so that we can know whether any more NA values are present in the data set or not. So see clearly you could see the 0 over here. Earlier it used to be 1. So this operation has performed the removal of NA value and replacement to 0. So now, as our data set is clear, let's check dimensions once again. Dimensions of players. Okay, 1034 rows are there in our data set and 6 columns. So let us calculate some key values like mean of the uh, age. Calculate mean value of age column. So here I am more focused towards the age column because I want to know whether the team players belong to some specific age group or not. So if so, we need to do mean of players age. Oh, it's players not found. So sorry. As R is case sensitive, we need to be very careful while playing with the variable names. So you could see the mean value is 28.7371. So this tells us that most of the players' ages average is 28.736. So let me store this uh, me, mean in age mean variable, which can be used further in our analysis. So so you could see over here 28.7. So after calculating this mean, uh, I just I'm just wanna present you the visualization plot of age versus team, uh, so that you could see like which team has more age players than other team. So this could be obtained by performing the following operation. Players, just I'm pipelining the data over here. Players ggplot ggplot of AES of x equal to, I'm just giving over here team, comma, y equal to age. So I'm just visualizing for team versus age of players using color as team, because we have many teams, right? It's really difficult to identify which player belongs to which team. So color equal to team. Mm, and I'm going to plot geometric point plot. So sorry, what's happening? Oh, this should not be color equal to team. This should be in this way. Yeah, this is good. So here you could see we have many teams like ANA, ARZ, ATL, BAL, BOS. There are many teams. But when you check it here, let me maximize this window. So if you could see here, NYM team has a player whose age is more than 40. So this team consists of like three players whose age is more than 40. Most of the team players uh, are below 30, and very few players are in between 30 and 40. Not few, it's significant, but very few players are more than 40 years old. So in this specific team WAS, there are no players who are more than 40, and there are also very less players between the age 30 and 40. This is quite interesting. I think this team has more chances of future winnings, I guess. I don't know about their winnings, but still, yeah, as there are many young people, this is going to be the key team in future, I guess. And see, most of the team members for uh, this CLE team also lie between 20 and 30 years old, some 25 to 30 years old over here. So in this way, we can check the data, uh, like we can analyze the data set properly by representing it in various ways. This is one of the way that we can represent the data set, but there are many other ways too. So for the time being, let's move into other parts of discussion. So as we have calculated age mean, so age mean, we can plot the age mean histogram, not age mean histogram, player's age histogram. So hist of players age, where is dollar sign, age. So this is going to give me a histogram of player's age versus frequency plot. So how many, this graph tells us how many players has the age of 25 and how many players has the age of 30. This is just a frequency. So uh, if you clearly observe this graph, this is not a normal graph, normal distributed graph, but it is slightly skewed towards right, but somehow looking like normal distribution, but not exactly the same. So let me plot density plot for this plot of density of layers H. Hmm. Here you could see that the plot is there is some discontinuity over here. There is a person who is more than 45 and very close to 50 years old. I think there's only one person, and very few persons are uh, more than 35. So the data is typically right skewed. So in order to normalize normalize this, like in order to represent the data in a clear way with marginal error, with very minimal error, let's do bootstrapping. So, bootstrapping is a concept which gives us the very clear results, because uh, this bootstrapping plays very crucial role while performing various kinds of surveys. So, as a survey, you could get only few results, right? We can't spend too much of resources on collecting the data from everyone. Suppose if you consider one state, and if you are going to perform a survey that who are interested in purchasing an iPhone, so you can't go near everyone, and you can't ask them whether you are interested to purchase iPhone. So in that case, you are going to obtain some sample. So you are going to select some streets, and you are going to few people over there and get the sample from them. So but this is not the actual population. So in order to get the accurate results, we will resample the sample we collected from the people, some specific localities. So suppose you have some 10,000 people in a locality, but you collected some thousand samples. So if you resample this thousand samples into 10 times, then you could get the better results and better approximation of what people think. So that's what bootstrapping does. We are going to apply the sample that we have collected to the mission, and mission will run resample, and it will produce some different results for every sample, and finally we are going to get the uh, desired output from it. So let's perform the bootstrapping over here. Let us perform bootstrapping of the data. So here I'm taking the value of n, which should be resampled for 10 power 5 times. So, and age, I'm going to bootstrap age column. So I'm defining as age bootstrap and numerical of n, numeric of n for I in 1 to n x underscore boot sample of players dollar h comma we are going to give the size of the uh, data set, like size of the column, how many values are present in that particular column, particular data set. And we are going to perform replace operation. Sorry, replace equal to true. So this should be capital again. And we are going to calculate the mean age bootstrap of I equal to mean of x underscore boot. So this typically performs the bootstrapping. What we have done over here is I'm just collecting a sample and I'm repeating this sample 10 power 5 times so that it produces a desired outputs. So we need to give the size of the rows, like players, how many players present in the data set, and we are just calculating the meaning and assigning it to age bootstrap column. So let us check the distribution now, how the distribution curve look like, how the histogram looks like. Histogram of age underscore bootstrap. Let's check. Oh, sorry. I think I haven't run this command. Enrows players. Enrows find function enrolled could not. Okay. There should not be S, I guess. So let me rerun again. Okay. Invalid first argument. Error in sample. Mm, replace probabilities equal to true. Let me check where this. So here you could see that uh, in the first argument, it is saying that first argument invalid first argument age. So the main mistake here is the case of the letter. We need to use capital A as the data set has capital A. So now let me run the bootstrapping model and let me try to. It's still running. It is taking some time as we are repeating it 10 power 5 times. It takes some time to get the results. Once it's done, we will plot the histogram. Yeah, it's done. So now we can happily plot the histogram for that bootstrap model. So if you observe this histogram and if you just recall that histogram which we have seen earlier, you could clearly differentiate the variation of histogram from both. Like here, the histogram is uh, clearly a normally distributed histogram, but whereas in that case it somehow resembles like chi-squared kind of histogram. So mm, here, our bootstrapping model performed really good and gave a desired output, which is really useful and without any kind of deviations in the data. We are really good to get the results. So, let me plot the density plot as well for this data. So, so let me do one thing instead of plotting. Okay, let's plot for the density plot of density of so age bootstrap. So so yeah, now I think the mean is also concentrated on uh, the original mean, like it is centered around the original mean, I guess. As we perform bootstrapping, sometimes this goes to the left side or else right side, but in this case, I think as our mean is some 28.7, I think this will comes at the center. Let me check for the original histogram where the mean lies actually. Where is our original histogram? Yeah, histogram of plot of density. So this is our original density plot. Let me add a B line of V equal to age mean, age underscore mean, comma, color equal to 4. So here, if you could see, the mean is not really centered about the plot. It is somewhere here on the plot. But whereas if you could see in the bootstrapping model, if you add the line, AP line of V equal to same age underscore mean. Let me run this first of all. So it is exactly at middle. So the normal distribution is centered around the mean, original mean, that too. It is not shifted to right side or left side. And let me add some color so that it would look good. Color equal to 2. Yeah, this is all about bootstrapping of the model. And let us calculate the quantiles for this data. Quantile of players players dollar each. So what this quantile function does is, um, it will tell us the information how much data is present below that particular quantile level. So if you could see, uh, around 75%, around 75% of the players lie below the age of 31 years old. Um, and around 50% of the people, that means a huge chunk of the people, lie below 27. That is below 27, like starting from 20 years old. And if you could see here, only 25% of the people lie below 27 to 31 years old, and only 25% people lie below um, 31 to 48 years old. So this quantile function is very much useful to check how much data is present in which particular region. In this way, we can get the results with quantile function. And let us perform t-testing here primarily. T-testing, perform t-testing, t-testing. So the main usage of performing t-testing is that it is used for hypothesis testing. So the results which we obtain from t-test can uh, give us really a very good information that can be used to eliminate the null hypothesis or else to accept the null hypothesis. So how could this happen? What is hypothesis testing, first of all? So hypothesis testing is a testing which is conducted uh, on a sample data. So suppose if I'm doing a survey in a year called 2021, and I got some results. So Suppose my 2021 survey, 2021 survey, let me comment it out. 2021 survey on a data set, on a data objective gave me 25 as mean. Whereas in 2022, if I do the same survey on the same data object, control C, control V, data object give me some 30 as mean. So now I am in a confusion, like whether my survey report is good or bad. So I don't know whether my survey is going to fail or else going to pass. How accurate my survey is going to result me the output. So this we can check with the hypothesis testing. As we don't know our 2022 results are true or false, I'm going to assume 2021 survey mean as a null hypothesis. So I'm going to take H naught as 25, and if we take H naught as 25, the alternate hypothesis here would become HA equal to is not equal to 25. That's what alternate hypothesis is not equal to 25. That means the observed mean in 2022, observed mean 2022 is 30. So if if we are rejecting our null hypothesis, we are accepting our alternative hypothesis that HA not equal to 25. So if HA is not equal to 25, our observed mean is going to be the correct mean. It's not necessarily this is the only mean it is saying, but to somehow we are coming to a conclusion that our observed mean is not false, at least not false. It's we can't determine at this point of time whether it is completely true or completely false, but to the most extent it's going to be the true one, true mean. That's what hypothesis testing is. So by performing t-testing, what we are going to do here is we are going to either reject null hypothesis or else accept null hypothesis. So let's check. Suppose my mean is centered around 28 point. Let's get the variable age mean. So my mean is 28.73 is 671. So this is 28.7. Uh, I will check whether my null hypothesis is 29 or not. So I'm assuming H naught value to be 29, and I am going to perform the t-test. T dot test of players age, comma, mu equal to 29. So you could see one sample t-test, a data equal to player's age, t-value is minus 1.9596, and data frame is 1033, I think 1033 records, and p-value is 0.05031. Mhm, mhm. So I think 29 could be the answer. Alternative hypothesis true mean is not equal to 29. Mhm. So as p-value is so much of small, like it is slightly greater than, but not so much greater than 5%. So in hypothesis testing, what we do is, if our p-value is more than 5%, we are going to accept the null hypothesis and reject our true mean value. That means we are going to consider uh, the last year's mean, like we are going to consider the mean as 29 instead of 28.7. So as there is more uh, very less difference between the considered assumed mean and true mean, I'm just going to take it as 30, so that you could clearly justify the value of p, and also you could clearly justify the confidence interval. So I'm just taking 30. So now you can see here, there is very less chance, like it is 16 zeros before 2 and 0.0002 2. That means the p value is very less. What this p value tells us is, like, this p value gives us the the information of the mean 30, that how many times this mean 30 occurs, like probability of occurrence of mean 30 this much times, like 0.00002 times this 30 will occur. That means we can clearly reject it, right? So we are going to reject the null hypothesis and accept the alternative hypothesis. True mean is not equal to 30. That means my mean is correct to some extent. That means 28.7 is correct mean of my data. This is all about t-testing. We can also find the confidence interval of this data. So compute confidence interval. So before computing this confidence interval, we need to know the dimensions of the data. So I will just calculate the dimensions using n rows. Mm, Just total number of records I want to fetch. Here, dimensions of layers, layers of 1, n rows, mean age over here, mean age, mean of layers, age. Now let me compute for SD, standard deviation, SDH, SD, players age. Let me run these comments quickly one by one. I have the code handy on my other side. Let me just bring that code here, and I going to paste out here, Control C. So here, what I'm doing is I'm just getting the mean and standard deviation and number of rows that we have in our data set. So I'm just going to supply those things over here to the formula QT. This is 95% confidence interval. I'm going to calculate 95% confidence interval. I just took 0.975 because as the distribution is two-sided, it is going to reduce by zero point 0.5, so that we will be getting the 95% confidence interval. So df equal to n rows minus 1 as per the formula, and the standard deviation of h by square root of n rows will give us the error. So marginal error, lower bound, lower bound mean income minus error. So what is this mean income? Sorry, mean age. This should be mean age. Sorry, mean age plus error. So let me run this command and check the confidence interval. So 28.473072 to 29.0035. This is the way how we calculate manually the confidence interval. Okay, as we are running out of time, let me get the code right over here without typing and wasting the time. Just I will fetch and I will fetch the results using this, and I will explain you the code instead of typing. So after finding this confidence interval, I'm going to do a linear model fitting, simple linear model fit. So I'm performing fitting between the weight pounds column and height in inches column, because if you see the correlation core plot of COR of what players, if you see the okay, could not find function core plot. So I think I need to install the function core plot. Install. I have the library of core plot. Okay, now the core plot is loaded, and now we can do our analysis. Oh, X must be numeric. I think we are messing up. str of players. So height in inches, weight in pounds, age. So all these three are numeric. We can happily input them. Height, weight, age. So 1, 2, 3, 4, 5. 3, 4, 5. 4, 5, 6, I guess. Mhm. Yeah, now you could see. Here the main correlation is between height and pounds. So if you can see clearly, there is something like zero point 0.6 correlation between height and weight, whereas age, there is very less correlation, that is that to negative correlation of some minus zero point 0.3. We are not considering this age column much. We are more focused towards this height and weight. Uh, and within these two, height and weight, uh, I could say that height is not a dependent variable, right? Whereas weight is a dependent variable. If the height increases, there must be a situation that muscle power increases and the overall body structure grows, and automatically weight should increase. So this is a dependent variable. Weight is a dependent variable, whereas height is not a dependent variable. So that's the reason I'm just plotting between the weight in pounds and height in inches, whereas weight is dependent, height is not dependent. That's the reason it is on x-axis, it is on y-axis. So let me run linear fit. So after running the linear fit, let me just plot the data for the linear fit. Control C, Control X. Layers is not substitutable. So it is saying that object of type closure is not subsettable. I think there is issue with the coefficient before, because I was not fetching this coefficient and I was accessing it. Basically, what I did is like I just gave here intercept and slope to fit the line, to draw the line. It is a very uh, straightforward line, which is y equal to mx plus c, where m is the slope and c is the intercept, c is the intercept. So y is the, that's what here we have. And if you can observe this linear fit, um, it is showing like inter coefficients is something minus 159.685, 4.901 height of height in inches. That means this line will cross the mm, this line will cross the axis at minus 159.685. And for every 1 unit change in x-axis, that means for every 1 unit change in height, there will be 4.901 units change in the um, weight. That's what here we can interpret from this linear fit. And let me run this and run this. So now you can see here the plot of linear fit. Like there are some, it is between height in inches and weight in pounds. All the data is super linear. Like all the data is present on top of line and on below of line. Very few outliers. Here you could see one outlier, and here one outlier. I can say that. So the data is almost good with this linear model. It is doing good job, I guess. So uh, without coming to the final conclusion, let's step into a few more things that we need to check before coming to the conclusion. So this is the same, just different way to present the graph. I'm just using here geom smooth method equal to LM instead of using intercept equal to coefficient of 1 and coefficient of 2. Uh, Let me just grasp the summary of linear fit. So in summary of linear fit, it is showing that formula call and minimum value of residual is minus 193.176. I think this is somewhere a outlying value which can't be seen over here, and the maximum value is 70. Maximum value is 70. Mhm. Okay. And here you can see that the first quartile is minus 12.978 and third quartile is 11.9898. That means it is performing some really good. It is centered around 0. And if you come down and look at the coefficients, uh, you can see that intercept is minus 159.6849, which is really no use in practical way. So in real world, this doesn't seems to be a very good one to fit a line. Uh, it is never going to happen, never going to happen that minus 159 is just a useless one. We can't get anything useful out of it. And height is inches, as I said. So what is this probability greater than t? This probability greater than t tells us, gives us the information of hypothesis testing again. So height in inches, if the line is at 0, hypothesis testing at 0. So as the mean is, as a probability is very l- less than 5%, we are straightforward going to reject height in inches, the slope of the line to be 0. That's what this says. Uh, Slope of the line at 0 is the null hypothesis for this probability greater than t, and we are going to reject the null hypothesis and accept the slope of the line to be 4.9, which is our actual slope. And if you come down, you can see the significant codes, how significant these values are. And residual standard error, which is a error calculated by summing up the values of residuals. And also it is shown as 18.77. That means 18 pounds for each and every player, uh, not for each and every player. The error is supposed to be 18.77. That means that is 18 pounds. That means I think this is really performing good. So there are no issues with this model I so far. And adjusted R squared is something that is very important when we perform multivariate analysis, whereas multiple R squared. mm, so that's what um, we can analyze from summary of linear fit. That is very interesting as well. So let me dig more. Let me just get the error 14.27028 linear fit of residuals. And let me plot the linear fit. So if you can see, I'm just plotting the linear fit. Mm, why it's not triggering? Yeah. So this is a graph which is showing fitted values versus residuals. Fitted values are nothing but the predicted values of the model, and residuals are the residuals which we got from the model. Um, if you clearly observe here, the line is almost parallel to the x-axis, and all the points lie on top and below of it. That means the model is performing really good. A very few outliers are present, that is 641, 834, and 237. These are not impacting much, but anyways, we need to remove these as well for a best accuracy. So that's what we can interpret from this graph. And let me close it, and let's switch to other graph, normal quantile graph. So this normal quantile graph also really gives a significant data. So most of the points lie on this line, which means our model is really good again. Very few, I think very small quantity, 834, 237, and 641, same points lie outside, are deviated from the line. And this is performing really great. Theoretical quantiles versus standardized residuals. So in this way, we can interpret this graph. And if you check other graphs, scale location, fitted values versus standardized residuals. So this is also a similar kind of thing where we are plotting the graph against standard deviation of standardized residuals. Here you could see everything is same as previous, and the model is performing good from here as well. Let's switch for another plot. So this is one of the crazy plot I could say, because see here you can see different things like Cook's distance something, and there are certain dots or here 0.51 something. But the most of this is leverage versus standardized residuals. These are not absolute values. You could see negative values as well, and there is a outlier 641. So from this plot, what we can interpret is that most of the values lie on lower side of the leverage. Uh, that means our model does not impact much even if we remove any of the outliers from this side. But whereas if you find any of the outliers on extreme right side of this, and if you remove that uh, point, our model is going to deviate a lot from this original fit. That's what Cook's distance tells us. Cook's distance is something that how much deviation that can occur when we remove a outlier which is on the higher side of the leverage area. So here from here, uh, as every other plot is saying, our model is good fit uh, with this plot as well. So entirely our model is good to go. Hmm. Let us also perform some cross validations. So in this cross validation, I'm just taking position as relief picture, come out filter. So I'm just determining cross validation for those two, and I'm getting dimension players, and I'm going to calculate the errors uh, using low linear model. That means linear model using leave one out cross validation. In this cross validation, what we are doing is we are just applying every value uh, to the low linear function uh, via this test observations, and we are just removing a single data every time while we are training the data, and we are predicting the model here, and we are calculating the error by applying this model. So similarly, we are also doing the same thing with spline model, and here we gave x equal to train x data and y data. We have df equal to 15. Df equal to 15 is something that is very unique uh, values among this data set for players weight. Sorry, and let's compare these two models. Let's calculate the mean error for spline, which is minus 0.09, and the mean error for linear, which is 0.426322. So I think linear model is somewhat better. Uh, it's more better because the was positive error is good to go with, but whereas spline model is resulting in negative error, which is not so great. Mm, but both the models are performing good. So this is all about my final project on baseball players data set. So thank you one and all.